Right. Welcome to my channel. Today we going to walk through uh, to the paper EfficientNet Rethinking Model Scaling for Convolutional Neural Networks. This paper written by these authors, and so let's start. In this paper, we systematically study model scaling and identify that careful balancing network depth, width, and resolution can lead to better performance. So they pointing out uh, that they want to study that basically they're saying that the network should be increases in the three dimensions: depth, width, and resolution. If we increase these three dimensions of the network, that can lead to better performance. Well, that makes sense. Obviously, if you are higher, if you are deeper depth, your accuracy would be increased. If you have wider width, the accuracy would be increased. If you have big resolution image, the accuracy would be increased. Based on this observation, now they proposed a method which is called effective compound efficient, and they apply that methods on mobile nets and ResNet. And to give you further neural architecture, they were saying that architecture search technique was used on the baseline networks. Baseline networks were MobileNet and ResNet, and they developed a family of models called efficients. And they're saying that the network was 8 into 4 smaller and 6 into 1 faster. So in the abstract section, basically they were saying that they emphasize that network, if we have a bigger network with all three dimensions, accuracy would be improved. So they are not developing a new network, they just uh, develop a new method, you can say, in proposed method, and the baseline network is MobileNet and ResNet. Okay, so introduction, they were saying that the first breakthrough was obviously ResNet in the advancement of computer vision tests, in which the ResNet is 18 to 200, from 18 layer to 200 layer, and achieve 84% accuracy on ImageNet. And that's the most common scale way by the depth. And other less common but increasingly popular is image resolution size. Well, we are back in 2019. Until that, there was only one technique. A famous technique was to go network deeper, and the second famous technique was not famous. It was less common, but there was technique that was big guys were working on was image resolution. In previous work, it's common to scale only one three dimensions. So again, they were saying that there's only one method. Either you increase depth, width, or image. So they were saying that is there any method to scale up habitual accuracy? And based on the observation, they have a method which called effective compound scaling method. Okay, now coming to the this section or this graph, I was very when I saw this graph, but let me walk through this graph. So the image A is a baseline network example. Sorry, in which it's a conventional network which has relation, layer, and channels. In B, there's a type of network which has larger width. In C, there's a type of network which has larger depth, like ResNet. And in D, there's a network which have larger resolution. But in compound scaling method, they have all of them. They have all of them. But how did they have? And now they say that, for example, if you're to alpha stand alpha beta with image size gamma, where alpha beta gamma are constant coefficient among small grid search in a model. Basically, alpha is width, beta is depth, and gamma is resolution. Compound scaling method input, well, they say if they are bigger image, then obviously the accuracy would be increased. And they have that over here they're saying that in 2017 these two authors these two these two boys both show there exists a relationship between network width and depth, but till that they said that there was no any person, any institution which have find something which have which connects all three network width, depth and resolution. So we demonstrated our scale network was just they apply their mobile their scaling methods on mobile nets and ResNet, and they use neural architecture such which is another whole topic. I'm gonna make video on that soon, to develop a baseline network, and they're going to scale it with their proposed method. I'm repeating, they're going to scale it with their proposed method to obtain family of models. How they what was the proposed method we will see in a bit. Okay, so over here there was some little thing that there were some networks whose accuracy is this accuracy is this, and now they've seen little work that first there was a AlexNet, and then there was a convert efficiency but increased by doing some techniques, and so uh, in this paper I'm studying model efficiency is super large. So there's just background. Okay, there are many ways to scale the model. Again, they emphasize till now what we have learned now. So the key point for the first half: scale and network depth with resolution architecture. Such method used to develop a new network model were ResNet 50 and mobile net. Before it the scaling was dimension. Now move back. Okay, so model scaling methods, they again said that there's only the one type method, but over here if I could do some zoom in. Okay, okay, they formulate a problem in which f is operator, y is output tensor, and w is spatial dimension. Basically these are they're formulating the problem in a mathematical way, and they come up with the equation number 1, where n is equal to f into x into height, width and resolution. The shape of input tensor to layer, there are 3 shapes. Okay, and so here what we are think, so the in scaling dimensions they have 3 things. First, it is depth. The intuition is that deeper convnets can capture richer, more complex features, generalize well new tasks. Well, that does make sense. That if you have deeper networks, and then you have then you can capture rich amounts, such as skip connection was a breakthrough in the ResNet. But the main point over here that they were saying that, for example, ResNet 1000 has similar accuracy as ResNet 50. So just scaling up depth in the network is not achieving the task. And further suggesting that accuracy improved, and they're further suggesting that impaired scaling, they scale the network depth, accuracy, dimension of return with deep network. Let me explain this to you. Here it is. Where is that? Depth. Okay, when the depth is 1.0, accuracy 2.0, and then 4.0. When depth was 4th, I mean, what does 4 count for? 4 count for something else, but just for the sake of the argument, 4 is a much deeper, but accuracy remains same. But again they get the accuracy when the depth was 8, and the flops is floating operation per second was so it was costing. Next thing, again they were emphasizing that only in the increasing of the depth would not be enough to achieve the more accuracy. What next? But it is width of the network, and then they say that features are easier to train. Again, it does make sense. However, extremely but shallow networks have difficulty in capturing high level feature. But if they are extremely wide, let me show you. If they are extremely wide but they are shallow network, this is shallow network but it is wide, so they're having a problem in achieving the accuracy. Now there is a graph over the accuracy that over 5 to achieve this accuracy, you can see over that. And then it's a resolution, higher resolution, input images, coordinate, and again, and the more resolution, the more accuracy it would be agreeing. So there comes number one observation: scaling up any dimension of network width, depth, or resolution improve accuracy, but the accuracy gain dimensions for bigger models. Meaning that only having in only the depth in one dimension is not fulfilling. So now compound scaling. We empirically observe that different scale dimensions are not independent. Intuitively, for high resolution images, we should increase network depth such that the larger receptive field can help fetch a similar feature that include more pixel bigger. Fine okay, in fact, paper with in this paper propose a new compound scaling method which use a compound efficient. Their composing method uh, phi, depth, width, resolution. Depth stand for alpha, width stand for beta, resolution stand for gamma, and alpha is greater than 1, and this is the formula where alpha beta are constants that they can determined by small grid search. Intuitively, phi uses specified coefficient. So of course notable flops of a regular convolution up in proportional. So they were saying that if they have bigger network, deeper network, it would be, yes, it would be in terms of cost it would be more. So over here suggests that we need to coordinate balance different scaling dimension. Over here they were saying that in order to pursue better accuracy efficiency, it is critical to balance all dimensions of network width, depth, and resolution. Right. So far, first they made an observation in which scaling dimension network depth resolution improve accuracy, and second they are making observation in order to pursue better accuracy and efficiency. It is critical to balance all dimensions of network width, depth, resolution during convolutional scaling. That it should be balanced approach in all dimensions. For example, with deeper D.20 resolution 2.0, width scaling achieves much better accuracy under the same flop cost. So over here now, EfficientNet architecture. Since model scaling does not change the layer operator in Bayesian network, we have baseline now over here. Break point 2. Scaling up and dimension network depth resolution improve. It's for our observation. Now let's go back to this thing. I think there's no need. Okay. Existing converter but doesn't measure in mobile. This called, we have also developed new mobile size called EfficientNet. Okay, so they are developing EfficientNet architecture. They're using baseline method. Now they are using new mobile size or convolutional which are inverted residuals, and they're using newer architecture such that optimize both accuracy and flop. So they're going to search or use that architecture with these parameters with the optimize with both accuracy and flops to make the architecture. Over here you can see the mobile net resolution channels, baseline networks, and you can see this table as well. Its main building block, the architecture has mobile inverted bottleneck. It's another thing we have to look, and it's another paper. You can look at this paper. This is mobile net, famous mobile net, and they added squeeze and excitation optimization. This is another thing we have to look. And but let's not talk about this thing. So to make any efficient net, step one, first we fix phi 1, we are using we are just assuming value. Twice more sources available to small grid search alpha beta y based on equation 2 and 3. In particular, we find the best value efficient mesh 0 as alpha 1.2, beta 1.1, gamma 1.15 under constant of alpha dot beta square dot gamma square coefficient is equal approximately 2. And step 2, we fix the alpha beta constant and scale up the Bayesian network with phi using equation 3 to obtain efficient net to efficiency. First, they will have equation by using equation 2 and 3, and then they put this thing in equation 3 so to get the efficient net 1 B7 network. Okay, scaling up as a proof concept, first apply our scaling method widely mobile net and ResNet, and we show image and result scaling. Then compare the single dimension scaling method, our compound scaling method proof. So they are saying they are comparing single dimension methods, our compound scaling method to accuracy on all these models. Over here you can see that accuracy. Now you can see the parameter efficient B0 5.3 million 1.1x. ResNet 50 76 26 million 4 into 9x bigger, and 4.13 billion 11 times bigger flops, 4.9 times bigger. You can say that 4.9 times bigger the parameters, and over here you can see that EfficientNet were smaller. In terms of resources, they are smaller in terms of parameter resources, and the accuracy is surpassed the other networks. This is a table, you can go through them, and then we train our efficient models image. They train the methods on ImageNet. So you're using RS prop optimizer with decay of 0.9 and momentum of 0.9, batch normalization, and initial learning rate 0.3. Say they use silo activation function and auto augment. Auto augment is a type of technique in which that we have neural network, which image augmentation is done by the network, not by just those parameter. This is another thing, and they are stochastic depth in which that you just miss some of the values. This is another bunch of topic we will talk about later on that. Then convolutional accuracy, our efficient model generally use an order of magnitude for parameters. In but EfficientNet achieve 81 with 66 millimeter, 66 million parameter and 37 million flops, and being and over there they say it will fall smaller than the previous best give by these gains. You can see that this network is small. They're claiming that all over there. You can see that, for example, our efficient B achieves higher accuracy than ResNet 101 using 18 into 18% flip flops. And of course, Bayesian model, original image Bayesian model, if you have deeper depth, wider width, compound scaling, result get better, and it's obvious results are better. So that's it, the basic emphasis of this network. So the key point would be that the thing which we have to learn about from over here is that the network is scaled up into 3 dimensions, and they did not develop a new network, they just developed a new novel method which is called compound scaling, and accuracy was improved. And then I will going to make a video in which I will try to implement the auto augment and these parameter only transfer learning, so then we can have a little bit look over that. Till that, thank you for watching this video, and if you have any question, comment. I will try my best to resolve to answer that thing. Thank you for watching it.